Dr. Baker has already introduced our talk. So I'm going to start us off by giving a fairly general and very brief overview of the state of our climate. So what you are observing, hopefully you're observing on your screen, is a visualization showing how global temperatures have been changing since 1850. And then this projects also into the future, showing what temperatures will be like by the end of the century. This visualization was put together by Ed Hawkins at the University of Reading. He's been doing a lot of work on trying to make climate change data more accessible. And so this is one way to visualize the data and the temperatures that we're observing. So the temperature changes that have so far been observed globally have been around 2 degrees Fahrenheit since 1850. And obviously this warming trend is projected to continue into the future. So I'm going to try to look a little bit more closer to home. And so now you're viewing the visualization that was also put together by Ed Hawkins showing the temperature change specific to the US since 1895. This visual is set up in a way that the blue colors show years that were cooler than a baseline. The baseline in this particular example is a 30-year average from 1971 to 2000. And then the red colors are showing years that were warmer. And the US trends are pretty similar to what the global trends are. There's some variation, but temperatures in the US have on average increased. The rate of change is about 1.5 or 1.6 degrees Fahrenheit per century. So this is the kind of general change for across the United States, but obviously I want to look much more close to the Nashua River Watershed. And when we look at the United States overall, we'll see that the temperature change has not been the same everywhere. So this map shows the rate of temperature change from 1901 to 2020 across the United States. And it should be fairly obvious looking at this map that the rate of change is not the same everywhere. And you can tell by looking at the Northeast in particular is one of the regions that has been warming faster than the US average. And so, yeah, sorry, I should put this out on the screen. So you can see obviously the Northeast up here, Massachusetts. And so we really are warming faster than average for the United States. Alaska is probably the only place that is warming faster, maybe in Southern California. Oh yeah, and I should point out the scale here. So we're looking at trends that are on the order of 4 degrees Fahrenheit per century in some regions of the country. So in Massachusetts, we're close to about 3 or 3.5 degrees Fahrenheit. So we are warming here faster than the US average. So looking even more closely to home, so I downloaded data that was relevant to the Nashua River Basin, but looking kind of broadly across central Massachusetts. So now we're looking at the temperature trend starting in 1895 up until 2020, looking at the temperature data for the central Massachusetts region. And the data are set up looking at the temperature change from an average value, again, using this baseline of 1971 to 2000. And so any temperatures that are above that line, shown in red, are years that were warmer than average. And then the ones that are shown in blue below that 0 are years that were cooler than average. And so again, we see a similar trend in central Massachusetts that is mapped out across the United States and globally. But again, we are warming more quickly in Massachusetts, and in central Massachusetts, it's even a little bit warmer than the average across the record. Looking in a little bit more detail about what our warming has been like here in central Massachusetts, I was looking at the rate of change across the seasons. And we see that even when we look just in our region, the warming hasn't been the same across the entire year. So this is, again, looking at that long-term record. This is from 1901 to 2020, looking at the rate of warming in the spring, summer, fall, and winter. And what we see is that winters are warming faster than the rest of the year. And so this obviously has important implications for our ecosystems, and also helps us to start to understand what some of the other climate changes that are important to the Nashua River are like. So for example, I'll show in a second some of the precipitation changes that have been observed. And with the temperatures warming, especially in winter, we can start to get a sense of how, for example, our snowpack is affected, and the fact that a lot of our precipitation the proportion of our precipitation in the wintertime is starting to come more as rain as opposed to snow. And that transition is projected to increase in a way that by the end of the century, some projections show that we will primarily have rain as winter precipitation instead of snow. So looking at more detail about the precipitation changes that we have been observing in this region. So this is a graph that came from the National Oceanic and Atmospheric Administration, showing the precipitation values from starting in 1895 up until today. And precipitation obviously is a lot more variable than the temperature patterns that we see. But we do see on average that the total precipitation that we experience here in the Northeast, especially in central Massachusetts, has been increasing. And that our precipitation, potentially more importantly, is becoming more episodic. So rather than having consistent precipitation across all of the months of the year, we're tending to have more dry spells that are then marked by heavy downpours, for example. And so those changes have important implications for things like soil erosion or urban flooding. And so we'll be hearing from Ralph about soils in next month. And then a lot of the changes that are important in terms of hydrology, there are a couple of talks towards the end of this series that would be focused more on hydrology. But the changes that we're seeing in precipitation, you can dig into a lot of the details. So again, overall, we're seeing the total amount of precipitation increasing, but the way that it's coming down, those changes are having pretty important impacts on our river systems. So the temperature and precipitation changes that we're observing obviously have impacts on our local ecosystems. And we're also seeing that our local ecosystems can respond in a way that either kind of amplify or moderate those changes. And so Chris is going to take over and talk in more detail about how forests are responding to these changes that we're seeing. So I will stop sharing my screen and let Chris take over.
Great. Thanks, Liz. Let's see here. Okay, share that. And do that and delete that. Okay. Greetings, everyone. Thanks for coming out so late at night for many of us to talk about climate change over Zoom. So I'm going to talk about, as Liz said, focus on what are some of the impacts we're seeing in local forests. So on the map that I hope you all can see, I've juxtaposed the Nashua River Watershed itself right onto the map of Massachusetts because I'm going to focus on two forest data sets here. Most of the data I'm going to talk about is central Mass, but it's not technically in the Nashua River Watershed. I hope that's okay. I'm going to present some data from Harvard Forest out of Petersham, Mass. They really have the best data exploring the questions we're going to be thinking about. And I'll show just one slide of data from some work I've done with a colleague at Fitchburg State, which is in the Nashua River Watershed. Either way, these are forests that are pretty typical for our region, as you'll see when we look at the data a little more here. Okay, there we go. And in particular, since we don't have a lot of time, I wanted to zoom in on what we call negative and positive feedbacks. Can climate change or can warming initiate either negative and or positive feedbacks? And what we mean by that in science, we don't mean negative being bad and positive being good. That's a way we use the term negative and positive in common language. But in science, when we talk about negative or positive feedbacks, a negative feedback simply means a change that occurs that will then counteract or cause a response that counteracts the initial change. So think of a negative feedback. A good example is in your home. If the temperature starts to drop in your home, that's a change. That drop in temperature turns on the thermostat, or the thermostat turns on the heat, and then the heat will come up, and then it counteracts the original change. So there's a negative feedback that negates the original input, and so you end up getting kind of a homeostasis from negative feedback. Positive feedback is the opposite. When there's some kind of a change, it causes a response that then increases the original thing in the first place. So a good example of positive feedback many of you have probably heard of this is not central Mass, obviously, but when warming reduces reflection from ice. So let's say our change in this case is an increase in temperature. Climates are warming, as you just saw from Liz. What happens there is it that can cause a decrease in ice cover. So we see, in this case, less sea ice over the Arctic Ocean. Same phenomenon would be decreasing ice cover on glaciers and things. Well, when you increase the temperature and you melt ice, you reduce the amount of reflection from the ice. So sunlight would normally bounce off mostly from a white ice surface. When you lose the ice, you get a darker water or darker land surface that absorbs that sunlight. And so so you're heating up more because you've lost the ice. That's a positive feedback. So the change, the warming temperature caused the change that's going to lead to even more warming. So and then my personal favorite positive feedback was published in National Geographic about a decade ago. These are sheep in New Zealand. Now, sheep have high reflection. They have high albedo or high reflection. They reflect sunlight. But because of the warming we're experiencing, people are not wearing as many wool sweaters in New Zealand. And so the number of sheep are going down, so there's less reflection. Now, if some of you are scratching your heads, if you pay very close attention, you notice this was in National Geographic on April Fool's Day in 2011. I point out this example partly because I think it's funny, but partly it's a good example where you have to ask yourself, when I first said this idea, did you kind of nod along and say, well, that makes sense? Sometimes when we hear something that's totally ridiculous, but if it matches our worldview, we don't realize how ridiculous it is. And that's a good warning, I think, for all of us to just check our biases and be skeptical when we hear new things. So I'll try to, for the rest of the talk, justify my data so you can be skeptical. All right, so back to our local forests. So can warming initiate negative or positive feedbacks, strictly focusing on forests? Well, you can have a negative feedback if the forest was to increase its growth. So that's an upward arrow. If the forest increases its growth, it's going to take up more carbon dioxide from the atmosphere. So if the carbon dioxide is causing the warming, if the forest then pulls a significant amount of CO2 out of the air, that's going to then counteract the warming. That's a negative feedback that could happen. On the other hand, there are changes in which the forest could actually end up releasing more carbon dioxide because it's getting warmer. And the obvious example there is increased decomposition rates. So when material is decomposing in the forest floor, in the soil, that's an example of soil, that's respiration. Just like right now, you are respiring away, you're releasing carbon dioxide from the food that you have consumed, you're getting energy from the food and releasing the CO2 from the food molecules. Well, decomposers do the same thing. They're doing respiration in the soils and they're just slowly releasing the CO2 from their foods. But if decomposition increases as a consequence of warming, that would be a positive feedback. I'm going to show you an example where I would argue there is one invasive insect that is more common because of warming, and it's contributing to a positive feedback. And we'll talk about some others at the end. But so if negative feedbacks are really important, then the forest is going to serve largely as a carbon sink. So the C stands for carbon. On the other hand, if positive feedbacks are stronger, then the forest is going to end up being a carbon source, releasing more carbon dioxide to the atmosphere. And the moral of the story is that currently, of course, as you all know, forests are carbon sinks. And so right now, forests are taking up a lot of carbon for us. They're doing us a lot of favors. But down the road, there is a risk of unleashing stronger and stronger positive feedbacks in the future. They've already started. They're just not as strong as the forest taking up the carbon at this point, but that could change in the future. So how are we going to study these feedbacks? Again, we're going to look at data over in Petersham, Mass, and a little bit from here in Fitchburg. All right, graph number one, data number one, we're going to look at measurements done at Harvard Forest. So most of these data are from a monograph by Finzi et al. out of Harvard Forest. And they measured forest growth, and they're going to define that as net primary productivity. So our NPP is net primary productivity. That's the official term for just how much stuff grew, how much plant growth was there. Roots, stems, tree trunks, branches, leaves. And they measured that in this data set. They measured it starting in the year 2000 up to the year 2014. So the y-axis here is total growth, net primary productivity. And they're focused here in this graph on a hardwood forest. So it's a typical central Massachusetts forest with mostly oak, some maple, beech, birches, probably a few pines in there as well. A typical hardwood forest for our region. And what you can see here is that the forest growth, the net primary productivity, is actually statistically increasing over time. So reaching up around 400 to 500 grams of carbon per meter squared per year. So that's what those units mean on that side there. So we do see a sign here of an indication that the forest is actually growing more each year. There's a little part of a negative feedback there. The forest is taking more carbon dioxide out of the air each year, at least in terms of tree growth. Now, why is that forest growing more and more? I guess if this was a class, I would stop and ask for input, but it doesn't work as well when we're doing a Zoom presentation. So you can probably guess, why is the forest growing more? There's actually a few reasons. The obvious one, as Liz already hinted at, is there's longer growing seasons, right? So spring is arriving earlier, fall is coming later. There's more time to grow. We're seeing the trees respond to that right here in our own local forests. Another factor has to do with the fact that there's more carbon dioxide in the atmosphere. Plants use that carbon dioxide to grow. So if there's more CO2 in the air around them, they actually ends up meaning they can use water more efficiently, because they have little holes called stomata that they open to bring in the carbon dioxide. Well, if there's more carbon dioxide, they don't have to open those holes as much, and that means they can retain more water. The plants can, so they can use water more efficiently and still grow better. So that's another factor. A third factor that's really important for the Harvard forest data is in their particular forest, and this may be a little bit more unique to where they are sampling. They've gotten more red oak dominating their data sets over time. So red oak is a very fast growing carbon dense species of tree. It packs a lot of carbon in, makes very dense wood. And because red oak was becoming more and more common as the large trees in their data set over time, that also partly accounts for the change you're seeing here. So it's not simply climate change, it's also just the change in the composition of the trees. And another factor they point out is air quality is getting better, and trees are going to grow better in response to having less acid rain, which is well documented, and less ground level ozone and things. A lot of air quality indicators have improved even over the time frame of since the year 2000. So what I've been talking about in that graph is clearly hardwood forests are growing, having a higher productivity than they did, say, 20 years ago. But what about hemlock forests? Some of you can probably guess what's going to happen to hemlock here. The same data set for hemlock forests here, net primary productivity over a slightly lower time frame. They started recording their data in 2006. But you can see up until 2011, the hemlock forest was not clearly increasing, but it was growing about as abundantly as the hardwood forest, around 400 to 500, in this case, 500 grams of carbon stored per meter squared per year. And then 2012, 13 and 14, there's a significant decrease in the hemlock trees growth. The chat, I was going to ask in the chat box if anybody could guess. I'm sure I'm preaching to the choir here. You all know what caused this. Hemlock woolly adelgid, which I've abbreviated there. The hemlock woolly adelgid arrived to Petersham in 2012, and you can actually see the footprint in the productivity of those hemlock trees. There is the curse, the cause of this. Hemlock woolly adelgid is an insect. This is a blow up. You can see it has 6 little legs there. Each insect covers itself with a little fuzzy woolly covering to protect itself from predators. So that's why it gets the name hemlock woolly adelgid. I saw a speaker at Harvard Forest about 5 or 6 years ago who said at that point, every hemlock tree in their woods is either dead at this point from the adelgid, or it is dying from the adelgid, or it is waiting in trepidation for the adelgid to arrive very soon. The adelgids are killing our hemlock trees, and I imagine you know that story. The connection to climate change hits on something Liz said. The adelgids don't like it very cold. These bitter cold winters slow them down and can knock them out. So if you look back when the adelgids first colonized or invaded Massachusetts, this map is showing when they first arrived in 1989 up until 2003. So what is that, about a 14-year period? The adelgids really were mostly along the coast and in the Connecticut River Valley, where it's a little warmer. They didn't like where most of us are sitting right now, north central Massachusetts. They didn't like the Berkshires because it's cold, right? We're up here on the Monadnock Plateau up here. It's chilly where I am. I'm right here in Ashburnham right now, and we didn't get adelgids until about 10 years ago. What happened is, as Liz pointed out, winters are getting warmer. As Liz said, the winters are warming even faster than the summers and springs are warming. And because we got warmer winters, the adelgid spread. And so if you look at this map, this is now the whole adelgid range, but there's Massachusetts. By the year 2005, the adelgids were in all Massachusetts counties and had started moving up the coast of New Hampshire and Maine. 2009, they're spreading inland, again, as we're warming. 2012, they're spreading farther north and west. 2018, it's the last map I have. You can see there, well, we've covered now most of New Hampshire, part of southern Vermont, and moving north and west. So in summary, for that part here, we have seen, oops, sorry, my screen is being covered by, Zoom is trying to be helpful, but it's covering my screen. We've seen that the forest growth has increased in the hardwoods dominated forests, but forest growth has decreased, downward arrow, when hemlock woolly adelgid has come in. Now, another factor here affecting carbon, though, is decomposition rates or soil respiration. And turns out those have also increased over the last 25 years in the Harvard forest data sets. So we know that as we've warmed these last 25 years, there's more decomposition going on due to that increase in temperature. And we know that there's been a huge increase in decomposition in the areas where the woolly adelgid has killed off those hemlock trees. And if any of you have seen a forest after adelgid has knocked out trees, it's pretty obvious there's a lot more decomposition going on. You have initially the needles falling to the ground, decomposing, then branches, eventually dead trees start falling to the ground. There's a lot more material to decompose. So the previous graphs only looked at just the growth of the forest, but we also need to account for this decomposition. And so the most important statistic really is the forest mostly in a positive feedback or mostly in a negative feedback. Really, this is the statistic, or this is the measurement that tells us that the net ecosystem productivity is simply the total amount of forest growth minus, so there's a minus sign, minus the amount of decomposition going on here. So let's put these together. And now let's look at, and what Harvard Forest has done is put those together. And then we're going to look at a graph of what's the total net ecosystem productivity over the last couple of decade or so. All right, so this is a very complicated graph. I'm going to take it piece by piece. We are looking on the y-axis at net ecosystem productivity again. So that's the total amount, the net of growth of the trees minus the total amount of respiration going on. We're looking over from 1992 to 2015. And we can got this for 3 different forest types now. We have our hardwood forest in red dots, our hemlock forest in blue dots. And then they also have some data on a clear cut where they measured these same statistics. And the moral of the story is that if you have a healthy forest, right, over the last couple of decades, last 25 years, healthy forests are clearly carbon sinks. So the net effect of all those positive and negative feedbacks is the forest is still absorbing a lot more carbon than it's releasing. So even though there's more soil respiration going on, the forest is growing more and more. And so you can see throughout this whole time period, the forest is accumulating roughly around 300 grams of carbon per meter squared per year. So that's not just tree growth, but that's the whole system, right? The soil is accumulating carbon, the soil is respiring carbon, but in sum, it comes out to about, say, 300 grams per meter squared. The hemlock forest was doing the same until the adelgid hit. And now in the last few years, because of the what we already talked about, the forest is actually releasing carbon. So the hemlock, in the forest where the hemlock adelgid has wiped out so many trees, that's temporarily a carbon sink, carbon source, where there's CO2 being released to the atmosphere. And obviously in a clear cut for the first 3 or 4 years, after a clear cut, there's a lot of decomposition going on. Those are also releasing a lot of carbon to the atmosphere. Those are carbon sources. And then after about 4 years or so, they start to become sinks that are pulling in carbon out of the atmosphere. So there's a lot going on in this figure. Moral of the story is a healthy forest is a carbon sink. So then the question that I've tried to wrestle with in Fitchburg, with the future forest that replaces hemlock, will it resequester the same amount of carbon? In other words, we know we're going to lose our hemlock trees. It's a matter of time. It might be another 10 years, but eventually they're going to die. I'm not aware of any great cases of resistance, at least among local hemlock stands. So our hemlocks in our watershed our forest that's dominated by hemlock trees will eventually become a forest dominated by hardwood trees and maybe some pine in there as well. So will that forest simply, once it's allowed to grow, will that resequester, will it take out all that, ultimately the same amount of carbon? So to study that, I've been doing some work in Fitchburg with a colleague, Jack Ludlam at Fitchburg State. We have 16 permanent forest plots. We're down in the north side of downtown Fitchburg. So this is John Fitch Highway through the center of my picture. We have some plots on Ringe Road, some behind the Fitchburg State ball fields, and then some behind the Civic Center. Each of these are 20 by 20 meter forest plots where we have measured every tree and down to really small saplings. And we're keeping track of their size and their growth. We also look at some soil pH. We look at number of saplings and things. But for this talk, I want to focus on soil organic matter. So one of the things we've been measuring is what % of the soil is organic matter, so organic carbon. What we do is we literally just burn the soil. So the top one has its organic matter. The bottom soil sample in my picture has burned off its organic matter. So it has that kind of rusty mineral soil look to it. And we're looking at the amount of soil organic matter versus the amount of hemlocks in the environment. So these are the forest plots on the right here that have abundant hemlock trees, around 30 to 50% or more. And we're measuring hemlock abundance as basal area. So because we've measured the diameter of every tree, we can measure the total amount of basal area. That's simply the area of the circle that makes up the base of the tree. And then we just add it up for the whole forest plot. And we say these are plots with a lot of hemlock abundance. And then we have plots with very little hemlock abundance. And as you can see from this figure, there's a lot less organic matter in the forest when it does not have hemlock trees. So I think of this as a positive feedback, because will the future forests simply resequester the same carbon? Well, probably not, because down the road, warming brought us the adelgids. They're going to kill off our hemlock trees, but as a consequence, the future forest won't take up as much carbon because the future forest won't have as much organic matter in the soil. So that's what we found in Fitchburg, and I'm relieved to say they found something kind of similar over at Harvard Forest, where they have a lot bigger data sets. What they do there, so they're measuring the amount of carbon stored in different parts of our forest. They have forest that's dominated by hemlock trees. So this is not just one hemlock tree, but this is the whole forest plot, a stand that's mostly hemlock trees. And then they have hardwood stands with, again, oaks and maples, among others. And again, if you look at the amount of carbon, just like we found, they found significantly more organic matter in the hemlock dominated forest. They also found, we didn't measure this, but they found significantly more carbon in the live wood and foliage of those trees. And they found significantly more carbon in the roots of the hemlock forest. So the moral of the story here is the hemlock forests have a lot of carbon. So the future forest, once the hemlocks are gone, the future forest may end up leaving more carbon dioxide in the atmosphere than our current hemlock forests do. And if that's the case, that would be an example of a long-term positive feedback where, again, the warming brought us the more adelgids. The adelgids killed the hemlocks, and so you're left with a forest that is not taking up as much carbon. And so you have more carbon dioxide in the atmosphere, which leads to more warming, and you've got a positive feedback. So that's something that's going on in the woods around us. It's also worth thinking about, before we leave this picture, just meditate on this figure for a moment. Look how much carbon is underground in the organic matter of the soil and in the roots, and look how much carbon is above ground in the vegetation. Think about that next time you go out well, you can't see your forest tonight, it's too dark tonight, but next time you look out your window or go out in the woods, what we usually think of as the forest, we're kind of biased to think of everything above ground, but realize there's just as much, if not a little bit more, carbon actually stored underground than above ground. And that always amazes me in our forests. Okay, so those are some data showing what's been going on over the last, say, 20 to 25 years, looking at the Harvard Forest data. What's the future bring? Well, the future brings a lot of uncertainty. Because we don't know if negative feedbacks, or we don't know if they're going to get weaker. We could predict they probably would get weaker, because eventually that increase in tree growth is going to be limited by soil nutrients. So we said earlier that forests are, our forests are, at least the hardwood forests are growing a little bit more each year. They're growing a little bit faster, but trees can't keep doing that indefinitely. Eventually they're going to start to be limited by nitrogen, phosphorus, calcium, potassium, right? So those negative feedbacks may start to get weaker in the future, or are likely to. And it's also likely that the positive feedbacks are going to start to get stronger, and that's going to leave more carbon dioxide in the atmosphere. So decomposition rates are going to get faster and faster as we see future warming. We're certainly going to see more spread of the adelgid, and we may have other invasive insects, although a lot of them are not related to temperature, like emerald ash borer and Asian longhorn beetle, and those are not as temperature sensitive, I think, as the adelgid. So I can't blame them on warming. But then one we have not talked about is fire. Fire would lead to positive feedbacks in systems where if increases in drought lead to more fires, that's going to lead to more CO2 in the atmosphere, which then leads to more warming and more drought. And you got a positive feedback. I'm not an expert on this one, but my reading of this is that I'm not terribly worried about it in our watershed. We're north central Massachusetts, doesn't seem to be a system where fire's going to be a major driver of much of these changes. That's a different story, obviously, out west. The California and Northwest fires are clearly climate driven. That's a clear positive feedback. Where we are, fire doesn't seem to be as much of an issue. There are more significant fires, say in Western Mass, in the Berkshires, and certainly in the some of the scrub habitat near Cape Cod and things, the pitch pine habitats. But where we are, I don't think that's going to be as much of an issue. But if fire does increase, that would be an example of a future positive feedback. All right. Where's my, oops, I lost my, there we go. What I want to do is zoom in on some data, some more data from Harvard Forest about what decomposition is doing, because they did a really interesting study here that I want to share with you. All right, so we're looking at a picture from Harvard Forest taken in January, I think, of 2008. What they've been doing out there are putting out a series of plots where they have warmed the soil experimentally. They've added about 5 degrees Celsius to the soil since 1991. So 5 degrees Celsius, if that's a little bit higher than the typical projections in the next, say, 100 years, but it's in some models that we could realistically, oh God, we hope not, but we could realistically see that level of warming maybe in the next century. And so what Harvard Forest has been doing is putting out cables to warm the soil. It's actually a technology they got from the football stadiums. Outdoor football stadiums put warming cables in their turf to keep it from freezing. And so Harvard Forest used the same technology to warm the soil 5 degrees Celsius higher than the rest of the soil every year. Actually, if you think of that reflection slide we saw earlier, you'll notice that when it's warmer, this soil is also going to get warmed more by the sun because it's not reflecting as much sunlight. But I want to focus on the carbon results. And what they found is that on average, since 1991, the soil has lost on average about 60 grams of carbon per meter squared per year. It lost a little bit more early in the experiment, and then that changed, it slowed down. But on average, it's been about 60 grams per meter squared per year. And what that comes to is a loss of about 17% of the whole organic carbon in the soil over the 26 years of the current data set. So 17% of all that organic material in the soil is gone because the soil has been warmer. Well, let's go back to, we said earlier, there's a lot of organic matter underground. So 17% of this has disappeared from the warmer soils. So that's where these positive feedbacks in the future could start to get stronger and stronger as we release more of that carbon out of the soil. That then adds more CO2 to the atmosphere, which then leads to more, it's a greenhouse gas, which leads to more warming. You see how that works. So this is a pretty significant thing because, again, there's so much carbon stored in the soil. As we said, in our forest, there's just as much underground as there is above ground. What's disturbing on a global level is that globally, the carbon pool is actually larger than all of the vegetation and atmosphere carbon combined. So think of all of the forests on Earth, all of the grasslands and things, add up all their plant material, and then take all of the carbon in the atmosphere. That together is still a little bit less than all of the carbon that's in the soil as organic matter on the planet. And the reason it's only about 50-50 in our forest is we're a little bit atypical, but globally, if you look at, say, boreal forests up north of us, they have a lot of carbon on the ground, underground in the organic matter. You look at grasslands, which cover a lot of the planet, they have much more carbon underground than above ground. So that's why this global average says there's a lot underground. So awakening these positive feedbacks in the soil or releasing that carbon through increased decomposition it's the kind of thing that can keep some of us up at night. And then a little bit more bad news before we see something more hopeful. But in addition to these feedbacks or positive feedbacks, there's also a lot of uncertainties in terms of threat multipliers. So we want a forest in the future that's going to be able to grow and pull that carbon out of the atmosphere. But we're making it hard for that forest to migrate and keep up with climate change. Our trees need to move to keep up with the climate zones where they are adapted. And in order to move, they have to disperse their seeds and keep going, in our case, north. But we now have a lot of habitat fragmentation, right? We have human infrastructure that is in their way that was not in their way when they dealt with warming at the end of the last ice age, and that was a much slower warming. So everybody's probably thought about that one. One you may not have thought as much about, just was published last month in the journal Science. Another threat multiplier, making a challenge to our trees to keep up with warming and a challenge to migrate, is the defaunation, the loss of animals. So for example, this was, like I say, just published last month in Science. The effect, the loss of animals is affecting plants' ability to disperse their seeds and keep up with, move their range for climate change. Many of our plant species are dispersed by birds. In the tropics, many are dispersed by bats. Mammals are important dispersers of certain fruits. And as you know, certainly with birds, we've seen a huge decline in birds, and that defaunation, that loss of some of these animal dispersers is impacting plants. So plants are kind of getting hit with this double whammy. Not only is the climate changing faster than they've ever seen before, but they're losing many of the animals they need to help, at least the animal dispersed plants are losing the animals that help them disperse their seeds. So that's a threat multiplier. Okay, so I didn't want to end on the depressing stuff. I wanted to think about, so what can we do? Well, of course, we've been told what to do by this guy, at least for 50 years now. So we had to protect the forest, right? And so let's come back to this graph that we looked at earlier. So this is net ecosystem productivity. This is the total amount of carbon that's either being released from the forest system or being stored, taken up by the forest system. And as we said, an intact forest is actually taking up a lot of carbon. It's a sink. And we can say on average, this is probably a conservative estimate, but on average, it's a little bit over 300 grams of carbon per meter squared per year. So that's what a healthy forest is taking up. So that's what's going on in the forests in your hometowns. Well, we can multiply that number by 3.67 because that tells me the amount of carbon dioxide in the air that's taken up by that forest. So in other words, the 300 grams of carbon in each tree or in the organic matter in the soil, each atom of that of carbon came from CO2 from the atmosphere, being pulled out of the atmosphere. So carbon dioxide weighs 3.67 times as much as one carbon atom. So I know this number up top here, I can use that conversion to say, roughly there's 1.1 kilograms of carbon dioxide taken out of the air every year by just 1 square meter of forest. So just meditate on that for a minute. Picture a 1 square meter of forest. A healthy forest is pulling 1.1 kilo of carbon dioxide from the atmosphere every year. And that's our local forest. Okay, well, what you can do with that is there's a website called the Cool Climate Calculator, and I'm going to copy this link into the chat box as soon as I'm done talking here. We'll take questions and things in the chat box, so I'll copy this link so you don't have to try to write it down. What the calculator does is it tells you what is your whole household carbon dioxide emissions. And so this is not my house. This is just a standard. The default it offers you at first is is for sort of a standard American family, I think with 2.5 residents in it. But it takes about 10 minutes to go through this website. You'll plug in where you live, how you heat your home, how much fuel oil do you use, how much your electrical bill, what do you drive, what's the mileage in what you drive, how often do you travel by air, what do you eat. You fill out this website, and it's beautiful because it spits out how many tons of carbon dioxide equivalent does your household produce each year. And those are metric tons. And so that would be thousands of kilograms of CO2. So if you think of that graph we just saw, we said the forest removes 1.1 kilograms of CO2 per meter squared per year. Well, if this household is emitting 50,000 kilograms, you can just do the simple math there, and you would end up with, it would take about 4.5 hectares. I think in hectares, that's a hectare is 100 meters by 100 meters, but it comes out to about 11 acres. So it would take 11 acres of a healthy local forest in our watershed to sequester the emissions from this household. So this is a fun website to play with. I use it with my students because you can actually ask yourself, how much intact forest do I need to protect to offset my household's carbon emissions? It's not going to be real precise and accurate, but at least it gives you a ballpark. So I'll put that link up when I'm done here. So the moral of the story is, yeah, all right, what can we do is protect intact forest. Just want to end with a little bit of data since we have about 2 minutes. Mass Audubon has this great report called Losing Ground. They put it out every few years, and the last one came out just as COVID was unleashing on us in 2020. And a couple of quick statistics from that is that our state has been losing about 13 acres a day of habitat, 13 acres of forest. A lot of that is forest loss, and it's mostly in this sprawl frontier, which covers a lot of our watershed. So 13 acres a day is a little bit more than what we would need to sequester that carbon we just talked about. The good news is that loss of 13 acres a day is a lot less than it used to be. From the 1980s to the early 2000s, we were losing about 20 to 40 acres of natural habitat each day, according to their work. But the bad news of the recent forest loss is that 1/4 of it is actually cutting down forest to put up solar arrays. So according to Mass Audubon surveys, 1/4 of the recent habitat loss is actually putting up solar fields, which is really not, well, that's pretty obvious. So the last slide here, protecting our typical forests are around 80 to 120 years old, much like the Harvard forest. I like, by protecting those forests for climate change, that's a solution that begets other solutions. So we're doing carbon sequestration, we're pulling that CO2 out of the atmosphere, that's good. But the nice thing is it leads to all kinds of other positive outcomes, like we're protecting habitats and biodiversity, organisms that need dead standing trees like snags, organisms that need fallen old trees that onto the ground. Like an old system like that has a lot of biodiversity benefits. We're also improving water quality in this watershed because most of the rainwater that's going into our watershed, into our rivers, is actually filtered through these forests and wetlands, but filtered through these forests on the way there. So the more intact forests we have, we're protecting our water quality. We're improving flood control. Liz earlier mentioned the huge fluctuations we're getting in rainfall. If we want to mitigate those, we want to have more intact forests and wetlands to help absorb those extreme weather events. And then, of course, forests have aesthetic and recreation values as well. So we've got a solution to climate change that begets other solutions not as related to climate change. Now, that said, I don't mean to obviously give the impression that we have to protect every tree and every forest. We need working forests, right? We're going to have to harvest firewood and lumber somewhere, but there are ways to harvest in ways that maximize carbon storage in the system. There are ways to do it, and there are bad ways that maximize carbon loss. So we got to work on that. But so I didn't want to give the impression that we want to just harvest all of our wood down in the southeast and not get any lumber up here. Obviously, we need lumber, we need firewood up here too. But I wanted to just praise the work of folks like Nashua River Watershed Association and others that are working on forest protection as well as working in the water because of all these benefits here. So with that, think I can stop sharing. Okay, now I can see faces again. All right. I was flying solo there. I couldn't see any faces, so I had no idea if people were laughing at my jokes or falling asleep.
That's terrific, Chris. And Liz as well. Appreciate that so much. It's time for questions and answers. So if anyone wants to raise their hand, ask a question, we'll call on you.
Or you can put it in the chat. And there was one question from Liz's talk, and that was from Lori Nearing, and I will read it. She said, what about Alaska compared to New England, also warming very fast? And she's wondering why.
Yeah, okay, so that's a great question. In general, the Arctic region is warming faster than anywhere else on the planet. And that is related to partly because of the temperature changes tend to be a little bit moderate in the tropical regions. And so as you get farther north, changes tend to be greater, but it also has to do with some of the feedbacks that Chris just highlighted. Those feedbacks are happening at a pretty rapid pace in the Arctic as well. For example, releasing carbon from forests, from permafrost, and other feedbacks that are happening.
Okay. Thank you.
Yeah, thank you.
So-
Who else?
Let's see, we have another question. Should we focus on culling hemlocks from a forest? From Lee Hort.
So this is my personal opinion. I'm no expert, but I say no for two reasons. One is that we made that mistake with chestnut 100 years ago. People harvested all the chestnut in a panic, and we never found out if there was any resistant chestnut trees. We never gave them the chance. So I would like to let things play out. There are reports of kind of almost resistant stands of hemlocks. I forget where, I want to say parts of Connecticut, but they're not truly resistant, but at least they're dying very, very slowly instead of dying rapidly. Another reason to wait is that with many pests, the adelgid is an insect, and when it's abundant for a long enough time, there's a good chance something's going to come along that will kill the adelgid, either a virus, bacteria, fungal disease. Birds are learning how to eat these things. So if we give it time to kind of play out, it may, much like gypsy moths, right? It may kind of, not that gypsy moths don't cause any harm, but they're not nearly as bad as they were in the 1980s because they became so abundant that diseases kind of came in and knocked them back. And so I think it would be unwise to just go and cut all hemlock trees as a sort of proactive measure. But that's my personal opinion.
Okay, Lay said, phew, these are gorgeous, and I have some sentinel trees that I hope will survive. Thank you. And from Lori Sable, why are solar fields so bad, according to Chris? At least when forests are cut down to site them.
The last part, yeah. I'm not dissing photovoltaic energy. It should go on rooftops and it should go on parking lots. That's what Mass Audubon advocated for. Put your photovoltaics on a parking lot and cover the cars. That's great, but why are we cutting forests down and releasing the carbon to the atmosphere so we can make photovoltaic panel farm or fields? That's crazy in my opinion.
Okay, so this is from Todd. There are biocontrol agents that are being experimented for woolly algae control.
I'm not familiar. If you want, you
want to expound on that, Todd? You can just unmute yourself and speak up. Anybody can, if you want to.
Sure. Can you hear me?
Yep.
Yeah, I cannot remember the name, but there are insects that are native to the range where hemlock woolly adelgid originated from that have been looked at as natural enemies to the adelgid insect, and so there have been some experimental introductions of that biocontrol agent to just look and see the effectiveness at controlling infestations and hemlock. And so, anytime you're introducing something that is not native, of course, there has to be done a lot with extreme caution. We don't want to create more problems, but But it is one of the things that is being looked at for control of hemlock woolly adelgid. And of course, the name is, you know, some long complex Latin name that I can't remember. So I can't tell you what the name of the biocontrol agent is, but I know it's being looked at.
Thank you. So a question from Nancy. Jumping worms are devouring organic matter in soil and releasing carbon. What do you recommend? Horrible things.
I'm assuming it's directed at me and not.
Yeah, either one.
I don't know a way to get rid of the worms once they're there. I mean, one recommendation is try to make sure worms are not transported, especially as like, don't dump your fishing bait. The problem but that's not just jumping worms. That's been a problem with introduced worms. We don't have any native earthworms or night crawlers, is my understanding. Any place that was glaciated didn't have native earthworms. Those were brought over after European colonization, and I know they're an even bigger problem up in like Minnesota and Wisconsin, where they've actually consumed so much of that organic matter in the soil that they're really changing things. Plants are adapted to a thicker leaf litter to insulate them in the winter, and then the worms got rid of it. It's impacting salamander populations because the food the salamanders need are the insects that are in the leaf litter that's now gone because of the earthworms. So it's not just jumping worms, it's a lot of worms, but I don't know if you can get rid of them once they're there. Maybe, does anybody know a biocontrol for the annelids for worms like that? I don't know of anything.
Chickens? I don't know.
Anybody
Okay.
else?
I think I don't have any other questions in the chat. Anybody want to just unmute themselves and speak up?
Yeah, this is Todd again. I guess I have another sort of, I guess it's more of a comment than a question for Chris. Was just kind of struck by the juxtaposition of a couple of the central ideas that you talked about. First being, you know, the devastating impacts of hemlock woolly adelgid on our hemlock trees and what that means for the carbon balance of those forests. And then the kind of the message around forest protection and the importance of forest protection, which is, you know, I don't disagree that forest protection is very important for as a strategy for forest carbon, but protecting forests doesn't reduce any risks of losing our hemlock trees from those insects. And you know, you could say that about just about any forest health threat, that when forests are vulnerable to any kind of climate change impact, protection doesn't really do anything to reduce the risk of losing those forests or losing the carbon within those forests. And so I would just comment that there are, you know, active management, there is a role for active management there to reduce those risks, to reduce the vulnerability of losing the carbon in those forests. And there's been some interesting work looking at doing some partial harvests in hemlock stands where about 30% of the trees are removed. And when doing that, you open up the light availability in the remaining 70% of the trees that are there, and that improves the carbon balance so that those 70% of those remaining trees are much more healthier and stronger and are actually able to resist the hemlock woolly adelgid and mortality from the insect. So just I guess more of a comment than anything else that, you know, forest protection is really key, but there's also adaptation strategies and management that we can look to improve carbon and carbon stability in our forests as well.
Thank you. I totally agree. When I said protection, I didn't mean like don't ever cut a tree. I was thinking more in a sort of open space planning idea of designating areas that are just going to be protected sort of on a map kind of idea by the word protection. So thanks. And I totally agree with your point about the hemlocks. I think I heard something last weekend, the same with some gypsy moth oaks that were thin just a little bit or a little more resistant for probably the same reasons you're talking about. So I agree.
Interesting. Any other questions, comments? I have to say that the students at Fitchburg State University are very lucky to have both of you.
So,
As are we. So thank you.
so Martha, I have a question for Chris.
Okay, Marion.
And so, is there a tree or species of tree, Chris, that that you would suggest or recommend that we use to replant to take the place of the hemlock that is disappearing, that would provide much of the same benefits?
Some years ago, some experts on hemlock adelgid recommended Norway spruce. It's not native, but it does create the same kind of dense shade, and it supports many of the bird species that rely on a dense hemlock habitat like that. So I've heard that recommended, but it's not native. So, and it sounds like Todd has a lot of background on hemlock. So Todd, you want to weigh in?
I could.
Yeah, well, I guess just a comment about Norway spruces. From my understanding, Norway spruce is we're kind of reaching a threshold with warming that might kind of be putting Norway spruce at a disadvantage. I know that's been planted a lot throughout New England, and there some places are seeing some dieback of Norway spruce just because of the temperature increases. So yeah, I don't know what there isn't really a good replacement to hemlock, unfortunately. It's a special tree.
And I know there's some birds, especially, was it black-throated green warblers and maybe the black-throated blue warbler? I forget. There's a couple of those that preferentially nest in that kind of habitat. So maybe we need some bird people to tell us where else will they nest, and that's the answer to your question, Marion.
I can share with you that Harvard Forest produced a book called Hemlock a few years ago. It's a monograph of a lot of different papers that folks there working on hemlocks have compiled. And there's a lot of evidence that black birch seems to be doing quite well in the same places that hemlock has flourished. It's not quite as much of a keystone species as hemlock has been, but it's shade tolerant, and if you notice, there's a lot of black birch growing in many of the same places where hemlock grows. So that seems to be the one that's poised to assume some of those niches.
Thank you. Oh, here's from Mark Archambault, our former Smart Growth Circuit writer for NRWA, said, yes, black-throated green warblers favor hemlocks.
Thanks, Mark.
Yeah. Someone asked if they will be able to access the recording for this program, and yes, you will. We will have a copy of that. And we'll send it out to everybody who has registered, and you can share it amongst yourself. I think we'll probably also have it on our website. And Daniel Welsh, I think your colleague, if, as Liz said, the winter precipitation transitions more to all rain in the future and less snow, should we be thinking about planting trees that are also able to handle more swampy grounds?
Chris, do you have a better sense about the trees that can withstand swampier conditions? Or
My guess is that we're talking about a season when they're not really growing anyways. So and then they're gonna face periods of drought, as you were saying. There's just a lot of variation there. So probably you just want trees with a wide range that can handle a lot of variation.
Right. Well, thank you. I'm going to share our slide of, Michelle Gerard. I guess one more. Won't there be a lot of runoff with more rain in the winter?
yeah, I mean, that is one of the concerns, that the changes to the hydrology. And as I mentioned, and I know, Martha, you're about to talk about, the other talks that are in the series, the last two talks, I believe, are focused very much on hydrology. So
Okay, I'll take one more. This is an interesting question. So from Lee Hort, does anyone know if the Commonwealth will change the focus of forestry plans from lumber harvest to sustainable forestry planning? I think that's a $64,000 question for many people.
So Martha, I have another question, and this is regarding a comment that Chris made, which is of concern to me too, and that is where trees are being cut down to make way for the planting of solar panels, and so I would like have Chris to comment on or to give us his suggestions as to what we might do to prevent that from happening on a local and state level.
So somebody here may have more experience with the Mass Audubon losing ground, but one simple change, and this may have already happened, but is to get rid of the incentives. Right, there were state incentives for creating photovoltaic fields for good reason, because it's clean energy. But does anyone know if they've gotten rid of I thought there was going to be a statewide change, so you don't have the incentive if you're cutting down a forest to put up solar fields. They should go on parking lots and they should go on flat roofs. Does anyone know if that change has happened yet at the state level? I thought it was coming.
Michelle Gerard is saying Zara Dowling at UMass is researching this and recommending changes in zoning.
Zoning, okay.
And go ahead and speak up, Michelle, if you want to. I see you raised your hand.
I think there have been some changes with the incentives. I don't know if they're enough. I think DOER got the message that when you make it easier to clear cut, to build, you want to incentivize it in the opposite direction. But Zara Dowling is working, is doing research at UMass, and she and others speak to this topic of municipalities trying to plan and prepare and create zoning bylaws to help control where and when, where solar arrays can go. So I don't know enough about it to speak with a lot of accuracy, but I do know that work is being done in that area.
I can add something. There's a bill currently in the legislature, H4331, which would, it's a bill to let municipalities reasonably regulate solar farms. And this would basically give local control over more to the municipalities to limit or, in some way through their ordinances, have a greater control over where solar farms are sited. So I would ask you to call your legislators, as I have, and ask them to please co-sponsor H4331.
Okay. So just one more comment. Mary Metzger says, I heard a program last week from Mass Audubon. Most spruce and birch are moving north, and forests will be transitioning to oak and hickory. Thanks, Mary. So I'm going to go ahead and share our screen that shows the other programs that are coming up in the next parts of our series of talks on climate. So what we have coming up next is a talk by Ralph Baker, Dr. Ralph Baker, Getting to Know the Soils of Massachusetts and Why It Matters. And then we have two people from the New England Wilderness Trust who will be talking about wild resilience in April. And in May 26, we have impacts of climate change on our rivers and streams, and that's by Sarah Whiting, a water resources engineer. And then on Thursday, June 9th, we have torrential rains from slow-moving tropical storms. Is it the new normal? And that's by David Valley, who's a hydrologist at the National Weather Service. So I hope you can join us with for these programs, and you sign up the same way you signed up for this talk.